Hello guys, this is part one of a three-part series on how to analyze a truss bridge. And what this particular video talks about is static determinacy. And that is whether or not we're even able to analyze the bridge and predict what kind of tension and compression is going to be within each beam. First thing we need to talk about is the idea of compression and tension. And you know that if you compress something, it's being squeezed inward from both sides, right? You can't squeeze inward from one side or pull outward in tension from only one side. It has to be pulled or pushed inward from both sides. Now, what we're going to do is look at our trusses, and most trusses are comprised of individual members or beams, and they're usually joined by welds, or as you've learned with your wooden trusses, gusset plates. Now, those gusset plates, as I mentioned, are typically either wood or steel of some sort, but they could be made of a variety of things. Here is the roof trusses of a typical, could be a garage or a home, and you can see how all those beams are arranged. They call that a stick building, and they basically call the 2x4s that are being utilized as sticks. And it's an inexpensive way to construct a building because 2x4s are not all that expensive, or at least weren't before. And if you design it properly, you can hold up a lot of weight with an inexpensive layout of beams. Here's a airfoil or a wing, cross section of a wing, and you can see here all these small beams. Now this is really usually cut out of one piece or welded together if it needs to be, but you can see all of these different geometries are designed specifically to withstand the forces that are acting on a wing, which is usually an upwards lift. And so to distribute that throughout the structure so that the wing doesn't fall apart is an important thing. So trusses, or at least the design of a truss, the engineering behind it can be applied in a variety of ways to withstand pressures or loads. Now, what you'll see here is a typical railroad bridge, and I want to point out to you the gusset plates right there. And I also like to point out that within each of those what we call beams, which would be the large pieces that are connecting this truss bridge together, are lateral, smaller truss structures, which prevents any kind of side-to-side movement. And that's a critical thing, and you'll usually find ones that are underneath also, depending on the application. So when we think of a truss, we think of triangles. And we're going to look at this, and I know you're thinking this is not a triangle. Well, here we can put together four beams, and we can pin them, which means we lock them together in the four corners. And this might look like a solid structure until you apply a specific force to it. And what you see here is that if you apply a force in the upper left-hand corner, it's just going to rotate like that. It's not a very sturdy structure. So you have to do something else to make sure you prevent any kind of rotation like that or movement. That's really what any static structure does, is if you strategically place all of your beams, you can stop any kind of rotation of that structure and continue it to be static, which is what you design buildings and bridges to be. So here what you can do is add a diagonal there, and what that's going to do is allow that force to be applied but nothing to rotate. Now this is something you need to look at for a little bit before you can understand it, but what you do, I think you'll see. We have two different types of supports, and one is going to be a pin. Now this pin usually means that you have some sort of beam locked in. All right, so That's kind of thing where it's not going to slide to side. There's no side-to-side movement or up and down movement. So what these arrows indicate are that you have some sort of forces acting in any one of those directions. There could be a force up, a force down, a force to the right, or the force to the left. So what we're going to include those in our calculations later as forces that are being applied to the beam. So again, that's usually a horizontal or a vertical force. Both can be applied because you're locked in place. And what that means is if you apply a force to the beam itself, then the reaction force is going to be the pin holding it in place. So all these are reaction forces to external forces acting on this beam. Now, a roller is allowed to move side to side. So it's free to move side to side. But of course, because it's on a surface, then your reaction forces could be up or down if the roller is placed on a surface. But of course, if it's placed against the wall, then you have the two forces that can be applied are to the right or the left. Essentially, it's perpendicular to the surface. The forces are. So that's an important thing to consider as we go forward. So a few assumptions that we need to make. And look, these assumptions don't apply to every single structure out there, but in a simplistic manner, we need to make a few assumptions to be able to analyze this. All members are straight, right? We don't have any curved beams, although they do exist and they are applied in a variety of ways. All loads are applied at the joints. And so that's an interesting thing too, because you could have a beam that has a load applied at other locations, but the analysis becomes a bit more complex. And so for now, we're going to make that assumption that we only apply at the joints. All joints are pinned and frictionless. So, as you have your beam attached to some sort of support, or any other joint, really, if there's another beam attached to it, we're going to assume that there's no friction here. And we both know, or we all know that there is over time, especially with corrosion and degradation, but we'll assume those friction forces are not there. If they were there, we'd have to take them into account in terms of resistance forces and reaction forces to rotation. Now this one is a little hard to believe, but we're going to have to deal with it. And the fact is, each member has no weight. Now you might think, what? These are 10-foot, 12, 20-foot steel beams. How can they not have weight? Well, they do. But in the grand scheme of things, when you design a large bridge, let's say a 100-foot span, when you consider the loads that are going to be on it, 10 cars, 5 cars, semi-trucks, and you're considering maximum loads that will support this, that the bridge can support, the beams themselves play a very small role. So percentage-wise, it's okay to say, you know what, we'll assume these are massless or have no weight, and then what we really want to know is, what is the effect of additional forces acting on this structure? So what we'll really want to consider is when you drive a truck over it, or snow loads, or 3 or 4 cars. So that's where we start considering what's going to happen to this bridge. The assumption is when you build the bridge, it's going to stand. What we will care about is what else is going to be on it. And we're going to talk about these beams that only can be in tension or compression. And when it comes to tension or compression, when they're in tension, remember that we have forces acting outward. And when they're in compression, the forces are acting inward, squeezing it. So these assumptions are simplified, and it just depends on the application in terms of how you're going to, what risks you might have by only assuming everything is straight or frictionless. because they aren't, but you can always build that into a proper calculation. Here is the relationship I want you to understand. So a statically determinate structure is one that can be mathematically solved with this formula. And you're like, what is J, M, and R? Well, J is the total number of joints, M is the members, that is the beams, and R is the number of reactions. So let's take a look. So we're going to apply that formula to this first truss, which looks fine, right? It looks like it can support a load. You can drive over it. And in this case, we're saying let's apply a 500-pound force to that at joint D. And so we're looking at this, and we want to decide whether or not we can determine what the forces are. So first thing we want to do is count the number of members. And that's 1, 2, 3, 4, 5. And then we can count the number of joints. We got 1, 2, 3, and 4. And then reactions. Now this is a little different. Put it in green. Now the reaction forces could be this. If you have, generally speaking, your reaction forces will be in the X and Y direction. So in each one of these cases, you probably will have the beams either in tension or compression. So they're going to be kind of pointing in two dimensions. They can go left, right, or a combination thereof. That's the kind of net force acting on there. The same thing happens with this joint at the fixed location. So both of those are fixed supports. They're not going to move anywhere. And so depending on whether these beams are in tension or compression, we'll pull them in different directions. But for each of those, there's really it's either, up and to the right, and there's two components to where the forces could go. A positive Y, negative Y, or positive X, negative X. So 2 per means a total of 4 possible reaction forces, 2 at each junction. So if we add that together, we get 2 times the number of joints equals 5, the number of members, plus the number of reaction forces. Those things are not equal, and so that is indeterminate. And you're probably thinking, well, why? I mean, it seems like we could do enough math to figure this out. Well, here's the deal. When you first install this, there's a lot of welding and attaching going on, whether you're using pins and gusset plates and all sorts of stuff. So you're going to lock that into whatever this distance is, whatever this span is. That truss is locked in. So imagine you did that in the middle of summer. Because it's so hot, the metal, steel, is going to expand a little bit. And so you're going to weld it in and everything might be fine. But when the temperature churns, even just 20, 30, 40 degrees, the steel is going to contract a little bit. And now what that's going to do is preload some stresses. And so you might have some, even before anything drives on it, you might have some built-in tension or compression just because you've locked it in, because your supports are both fixed. And that introduces a lot of variables that unfortunately are hard to quantify, because when you first drive onto this particular truss bridge, you might have some beams that are in torsion, some are compression, some are in tension, and that's before you even drive anything on there. And so that's somewhat indeterminate when it comes down to it. So our solution will be, instead of a fixed, put a rolling support. And so what that does is, now you have the same number of beams, 1, 2, 3, 4, 5, so M is equal to 5. And we have the same number of joints, 1, 2, 3, 4. Now the difference here is in the number of reaction forces. Remember that with this fixed one, you can either go left, right, or up and down, but you really got to pick one, X and Y. So there's there's movement in either the X or the Y direction. So there's two different reaction forces. You can't go up and down is the point, right? When you have forces that are acting at a node like that, a junction, your net force is either in the positive or negative Y direction, or it's in the negative X or positive X. So there's two choices, generally speaking. There's two over here. Well, when you have a rolling support, you really only have one choice. You either have a net force that's going in the positive Y direction or the negative Y direction. And so there's really only one choice there. So that gives you reaction forces equal to 3. And so that allows you to make a determinant. And so what that does is, why would we want a rolling support? Well, it's really when you drive over a truss like this, you want to make sure it doesn't rotate. So you really need vertical support. But you also want to let the structure breathe. Breathe under certain temperatures and pressures and things of that nature. Otherwise, like I said earlier, you're going to have some pre-stressed materials that aren't going to behave very well under static or dynamic moving loads. So this allows, for something like expansion joints, allow bridges that span certain things to be able to kind of move closer together or further apart based on the temperature, especially here in Chicago. So to end it here, we can look at a real bridge in Brockport, New York. And it looks like it has 19 joints, 35 members. If you'd like to count them, you may. And a pin and a roller as the supports. And so maybe we can put the pin over here and roller over here. Now remember, when it comes to a pin, you either go up or down or left or right. So it's two of those for a pin. For a roller, as you learned, you can really go up or down. That's it. So that's the number of reaction forces that are possible. So in this case, it's statically determinate, and if the numbers were a little different, we wouldn't be able to tell what's going on. You could build it, but to be able to predict its behavior would be a difficult thing. So hopefully this helps with your first assignment.